Hi, good morning, everyone. Good morning. Good morning. Good morning. So, are there any questions for me?
Excuse me, sir.
Yes.
Sir, tomorrow's paper, sir. Could you change the time, sir, please? It'll be 6:30 and it's a weekday, sir.
Ah, what? Weekday?
Yeah, weekday here in Saudi.
Okay. Fine. You send me a message, will you? I will make an arrangement for you.
I
So,
sent,
already.
sir.
Okay. 9. Guys, are there any questions for home? Any questions for home? No? Nothing? No questions?
So I asked for questions. You said we are not ready yet, ready for questions in this topic.
Ah, yes. What is the last subtopic we have done? About the binding energy for nucleus, right? Right. Guys, write on the next subtopic, nuclear fission and fusion. Nuclear fission and fusion. So guys, you know, nuclear fission is a larger nucleus splitting into two lighter nuclei is nuclear fission, correct? Which is what used to produce energy in nuclear power stations. And two lighter nuclei combining together to form a larger nucleus is nuclear fusion, correct? So nuclear fusion, what happens is the core of a star, the core of the sun, what happens is nuclear fusion. Two lighter nuclei fuse together, fusing, combining together. So that's why you call it nuclear fusion. So nuclear fusion is two lighter nuclei combining together to form a larger nucleus. So write about it. Nuclear fission is a larger nucleus. Nuclear fission is a larger nucleus. Splitting into two lighter nuclei. Splitting into two lighter nuclei. Splitting into two lighter nuclei of approximately equal masses. Of approximately equal masses. Releasing energy. Releasing energy. And below that, nuclear fusion is two lighter nuclei joining together form a larger nucleus. To form a larger nucleus. Releasing energy. Okay. Guys, then write down the next subtopic. Energy mass equivalence. Energy mass equivalence. A nucleon has a mass which is approximately equal to 1 unified atomic mass unit. We call it U. Within brackets, you can mention U. 1 unified atomic mass unit. And the mass of that is 1.66 into 10 to the power minus 27 kilograms. Full stop. The exact masses of a proton, a neutron, and an electron are given in table A. So guys, these are the masses, the actual masses of the subatomic particles, proton, neutron, and electron. You can see the reason why the mass of the electron is considered to be 0 is it is extremely lesser compared to the mass of the proton and neutron. So we do take that mass of the proton and neutron is 1 atomic mass unit, 1 U, but it's not actually 1. If you take the mass of proton, it's 1.00722276, slightly different from 1 U. Same thing with the neutron. So the mass of the neutron is slightly different from 1, which is 1.008665 U. Okay. Mass of the electron is 0.000548, which is even to 3 decimal places or 2 decimal places, it's still 0 U. So that is the reason we usually don't consider the mass of the electrons earlier. Anyway, take it down. Okay. Right. Done. Guys, write down a question.
So wait, so 1 minute, so please. It's 1 minute.
Okay.
So we are not supposed to memorize this, right?
No.
No.
Just I have given it for you to do the next question actually. And just to know that there is something like this. Okay, right. In 1905, Albert Einstein proposed that there is an equivalence between mass and energy. Full stop. The relationship between energy and mass or change in mass, m is given by E equals mc square. E equals mc square. Right? Where c is the speed of light. We have made this equation before, right? E is measured in joules, m in kilograms, and c is in meters per second. Okay. Right. You guys write down a question. Calculate the binding energy in mega electron volts. Calculate the binding energy in mega electron volts of a carbon-14 nucleus. Of a carbon-14 nucleus with a mass defect of 0.1097360. Okay. Wait, now listen. Guys, what is mass defect? What is mass defect? Loss of mass. I mean, how is it there a loss of mass here? Now listen, guys. Now, if you take carbon-14 nucleus, let's say it has a certain mass. Okay. Let's say carbon-14 nucleus has a mass of m1. Then it consists of protons and neutrons. I separate all the nucleons, protons and neutrons, I separate them. Okay. Carbon-14 has 14 nucleons. Okay. It has 6 protons and 8 neutrons. No? 6 protons and 8 neutrons, we separate it. So now, when you separate, let's say the mass is m2. Okay. Now, imagine Now I take a person. His mass is 60 kilograms. Okay. Now I cut his neck, his hands, legs. Okay. Whatever the other parts that I can cut, I cut. Okay. And there's no bleeding. No bleeding. Hypothetical situation. Okay. Then if I take those, listen. If he is originally 60 kilograms, if I cut them into parts, cut his parts, and if I collect those parts and measure the mass, there's no bleeding. Okay. What should be the mass of all those parts? 60 kilograms, right? But when you take a nucleus, it doesn't work that way. If you take the nucleus, if its mass is M1, if I separate all the nucleons, and if the total mass of all the nucleons is M2, M1 and M2 are not equal. Okay. M1 and M2 are not equal. So that difference between that M1 and M2 is what you call the mass defect. Understood? So what is meant by the binding energy? Binding energy. What is the definition of binding energy? We spoke about it, right? What's binding energy? The energy required for all the nucleons to be separated to infinity is what you call the binding energy. Correct? So binding energy is the energy equivalent to this mass difference. So the energy equivalent to this mass difference means we find it using E equals mc square. So you know the mass defect, 0.109736 U. You convert it into kilograms, multiply by 1.6 into 10 to the power minus 27, and then C square, 3 to 10 to the power 8 square. That will give you the binding energy in joules. Okay? Joules. So if you want to get it in electron volts, you need to divide by the charge of an electron, which is 1.6 into 10 to the power minus 90. That will give you the answer in electron volts. If you want to get it in mega electron volts, further divided by 10 to the power 6. That gives you the binding energy in mega electron volts. Okay.
So why did you multiply by the unified atomic mass unit?
Because this is mass defect is given in U. So for this equation E equals mc square, we need to substitute in SI units. So the mass has to be in kilograms. Is it 102.5? Did you calculate it? Sure. Okay. Let's take the tubes. Page 31. Question number 22. a nucleus of polonium 210 decays to lead 206 by emitting an alpha particle. The mass of the particles are shown in the table below. Polonium mass of the particles are given below. Polonium turns to lead and releases an alpha particle. So the energy released in this decay is about 9 into 10 power minus 13 joules. So guys, first I want to see the mass defect. So let me check the mass of the final products. Mass of the final products, if I take it as M2, that is lead and an alpha particle, which is 3.41918 into 10 to the power minus 25 plus 6.64437 into 10 to the power minus 27. So that is going to be the final mass is 3.4856. I'll take it to 5 decimal places. They have taken it to 5 decimal places. 3.4856 2 into 10 to the power minus 25 joules. Sorry, minus 25 kilograms. This is the mass after the decay. So before the decay, the polonium mass is 3.48572. So if I see the mass defect, delta M, the decrease in the mass, that is M1 minus M2. M1, the mass is 3.48572 into 10 to the power minus 25 minus 3.48562 into 10 to the power minus 25. 3.48572, 3.48562 into 10 to the power minus 25 is a mass defect of 1 into 10 to the power minus 29 kilograms. This is by how much the mass is reducing. Okay. So if the mass is reducing by this much, an equivalent amount of energy will be generated. Okay. Mass of the particles overall is reducing by this much, 1 into 10 to the power minus 29 kilograms. So then in this decay, the energy released will be equivalent to this mass, which is found using E equals mc square. M is 1 into 10 to the power minus 29 kilograms. Into the C is 3 into 10 to the power 8, and that needs to be squared. So 3 into 10 to the power 8 square it and multiply by 10 to the power minus 29. You will get exactly 9 into 10 to the power minus 13 joules. Sorry? Almost the same thing. So you're getting 9.6 into 10 to the power minus 30. I'm taking 10 into 10 to the power minus 30. When you took the mass defect, for how many decimal places did you find it? Problem is there. So all these masses are given for 5 decimal places, right? Okay, so I have taken the mass defect here. I also took it for 5 decimal places. Okay, so when I took it for 5 decimal places, I got the delta M exactly 1 into 10 to the power minus 29 kilograms. Based on what they have given, if they have given for 5 decimal places for these questions, you need high level of accuracy. So because the differences are very small, so take it to 5. If they have given the masses for 5 decimal places, you also take it for 5 dB. Okay. If they have taken for 3 dB in another question, you take it for 3 dB. Done. The exam is on tomorrow, unit 4 only. There's no unit 4 questions. It's a unit 4 paper tomorrow in the morning at 9 o'clock. So be here by latest by 8:50. Right, there's part 2. 98% of the energy from the decay is released as kinetic energy of the alpha particle. Calculate the velocity of the alpha particle immediately after the decay. So for the alpha particle, if I use E equals half mc square, half mv square, kinetic energy is half mv square. The kinetic energy is 98% of the energy released. Energy released is 9 into 10 to the power minus 3, minus 13. That into 98%. That is equal to half into mass of the alpha particle. The alpha particle consists of 4 neutrons, 2 protons and 2 neutrons. So it will be 4 into the atomic mass unit, which is 1.66 into 10 to the power minus 27. So this will be the mass of the alpha particle. That into V square. So get the V subjected from this.
So how do you get the 4?
There are 4 nucleons in an alpha particle, 2 protons and 2 neutrons. So I have multiplied the mass, atomic mass unit with 4.
Okay.
It's about 1.63 into 10 to the power 7 meters per second. They have given? Yeah. No. I didn't see that, sorry. You can take that, but I think it will be the same thing. Mass of the alpha particle is given. So you can just take that instead of what I have taken here. But I think it will be almost the same. Take that value what they have given. Okay. Right.
So instead of mass of a nucleon, can we use like mass of a proton?
Can't hear you clearly.
Instead of mass of a nucleon, can we use mass of a proton?
Isn't it the same? How is it different?
I mean, it's slightly different, right? 1.64.
1 point, no, it is the same. Check and see. But anyway, for this question, you don't have to use this. Forget about this. You can take this mass, they have straight away given the mass of the alpha particle. Use that one. But the next one, explain why not all the energy from this decay is released as kinetic energy of the alpha particle. Correct? Energy can be lost. Is alpha particle the only particle emitted here? Is alpha particle the only particle emitted here? Anyway, there can be fine. Now, when this now it is forming to polonium is decaying into lead, right? Lead and alpha particle, no. So won't lead have any kinetic energy? It also can have a small kinetic energy, right? So you can write also about it, right?
Excuse me, sir.
Yeah.
No, sir, because see, in the table video, the mass of a proton and the mass of a neutron is slightly different, right?
Yeah. That slight difference you can, if you want to take, you can take. But anyway, when we are taking the atomic mass unit, we don't consider that difference. We take it to 2 decimal places, 1.66 into 10 to the power minus 26. For 2 dp, if you check it, it will be the same. Okay.
Okay.
Right. So as mentioned there, the lead particle produced can also have some kinetic energy. Okay. Let's turn to the next one, 23. Can you give it a try?
Excuse me, sir.
Yeah.
So for this question, can we find the mass defect in electron giga electron volts and then convert that answer into kilograms?
Correct. That's what you have to do.
Yeah.
In 1935, Irene and Frederick, someone, were awarded a Nobel Prize for the discovery of artificial radioactivity. Okay, they bombarded an aluminium sheet with alpha particles to produce a radioactive isotope of phosphorus as in the nuclear equation below. Identify particle X. A particle with no charge and an one has to be neutral. It has to be neutral. Correct? No? Calculate the energy released in joules in this nuclear reaction. So guys, the mass before the decay is this alpha particle and this aluminium. Addition of those two, 3.7274 plus 25.1333, which is 28.8607. So the mass of the particles after the decay, this particle X and phosphorus, which is 0.9396 plus 27.9206. So that is 28.8602. So the mass defectives, the mass reduction in this nuclear decay is M1 minus M2. Five into 10 to the power minus 4. In the unit they have given, which is giga electron volts over C square. Am I right? So to convert that into kilograms, 5 into 10 to the power minus 4. To convert giga electron volts, first we have to multiply by 10 to the power 9 to convert giga electron volts to electron volts. And then to convert electron volts to joules, it is 1.6 into 10 to the power minus 90 over C square. C is 3 into 10 to the power 8. And that needs to be squared. This gives you the mass defect in kilograms. Which is 8.8. I'll take it for 5 decimal places, maybe 8889 into 10 to the power minus 31 kilograms. This is a mass defect. They want the answer in joules. So I'll use E equals mc square. That is 8.88889 into 10 to the power minus 31 into 3 into 10 to the power 8. That's squared. Is it 8 into 10 to the power minus 14? Are you getting this answer? Correct.
So one
Is that
thing
okay?
I don't understand how X is the neutron, sir.
Why it has no charge and it has a nuclear number of 1. No protons with a nuclear number of 1 means it has to be The neutron, right? What else can it be?
Okay.
Okay. Fine. Guys, part B. No. Right. Guys, the next part.
So without converting the mass to kilograms, can we get the energy in giga electron volts and then convert to joule?
Yeah. If you just take the mass defect, then it will be in giga electron volts. No?
No, sir, being giga electron volts over
Volts
C
per
square,
C
right?
square. Yeah. So that energy corresponding to that will be the energy in giga electron volts. Then you convert it into joules. Yes, that is also correct. You will get the same answer. Same thing. Right. There's the next one. Radioactive phosphorus was one of the first artificially produced isotopes to be used in diagnosis of cancerous tumors. The phosphorus 32 is injected into a person and collects it in the tumor. Radiation is detected outside the person's body, and P32 is a positron emitter with a half-life of almost 15 days. Explain why 32P is suitable for this procedure. Read it again. Okay. So what are they saying is this is used in medical physics. Radioactive phosphorus was one of the first artificially produced isotopes to be used in the diagnosis of cancerous tumors. The isotope P32 is injected into a person and collects in the tumor. Radiation is detected outside the person's body. P32 is a positron emitter with a half-life of almost 15 days. Explain why P32 is suitable for this procedure. Now,
Why
P32
should
is emitting what?
definitely be because it has a short half-life, right?
You can't call it a short half-life. It has a very good half-life. Not too short, not too long. 15 good days. Okay. So you can write about both actually. Wait. One is now it is emitting. What is it emitting? Positron. So when it emits positron, this positron annihilates with the electrons and produces gamma radiation. Gamma radiation has a high penetrating ability. So it can penetrate through the body. That has to be mentioned. Okay. The other one is, yes, talking about the half-life, it has a half-life of 15 days, which is not too less. And it gives sufficient time for you to do the treatment. And the other thing is, it is not too long. It won't stay in the body for years. And it doesn't create unnecessary dosage of radiation. So you can write about it's a 4-marker, right? The emitted positrons annihilate with electrodes and produce gamma radiation. Full stop. It can, no, that's positron. Hold on. It can penetrate through the body due to its high penetrating ability. Full stop. The half-life is not too short so it provides sufficient time to complete the treatment. And it is not too long thus it doesn't induce a high dose of radiation. The answer. Electrons, I should be
Say in a chain.
Okay, sorry about it. Let's start with the next one, 24 part A and B. Yes. Analysis. And there's another part also that we haven't done in this C part to complete that also in the same question. Right. There's the part A. Cesium-137 is a radioactive isotope produced during the fission of uranium. State what is meant by fission. A larger nucleus splitting into two lighter nuclei of approximately equal masses releasing energy. Okay, a larger nucleus splitting into two lighter nuclei. Releasing energy. Wow. Cesium-137 decays by emitting beta radiation. Complete the nuclear equation for the decay of cesium-137. So guys, beta particle is -10. So the barium will be 56, 137. Okay. Explain why the emission of an antineutrino in decay leads to a range of energies for beta minus particles. So guys, what happens here? Now the cesium that is stationary. So when it emits a beta particle, okay, for the momentum to be conserved, this cesium nucleus will recoil. Okay. If the cesium will recoil, but now there are three different particles which is being emitted: barium, the beta particle, and antineutrino. So now the total energy has to be shared between these three or these four. So it will be randomly shared. So they're asking why it leads to a range of energies for beta minus particle. It will not be the same always. It's randomly distributed. So if it happens once, the beta minus particle will have a certain amount of energy. When the same decay, when it happens again, this beta minus particle will have a slightly different value. It is random. So write the answer. The momentum is conserved. The momentum is conserved. And the cesium particle will recoil. Full stop. The energy released is randomly shared among the three particles. So the beta minus particle will have a range of energies.
So what do you mean by the cesium particle will recoil?
We have done the parts C part 1, C part 2. Cesium-137 may enter plants grown in the contaminated area. The radiation from 100 grams of plant material grown in a contaminated area can have a count rate as high as 500 becquerels. From 100 grams of plant material can have a count rate as high as 500 becquerels. The count rate of 150 per minute is considered safe. Determine the time taken for the count rate from 25 grams of plant material grown in a contaminated area to fall to a safe level. Right, whereas in 100 grams, the radiation from 100 grams of grown material can have a count rate as 500 becquerels means. Then in 25 grams, it will be 1/4 of that, which is 125 becquerels. Okay. The count rate, this is the initial count rate. A count rate of 150 per minute. Activity is 150 per minute means that is 150 over 60 per second. Correct? 150 over 60 is 2.5 per second. Per second is what you call becquerel. Am I right? The activity per second is what you call becquerel. So they basically what we need to find is the time taken for this activity of 125 becquerels to fall down to 2.5 becquerels. Yes or no? So A equals A naught e to the power minus lambda t. If I take the log version of it, ln A equals ln A naught minus lambda t. That is ln 2.5 equals ln 125 minus lambda. What is lambda? We have found lambda in the previous part, which is 7.286 into 10 to the power minus 10, is it? 7.286 into 10 to the power minus 10. Into 10, that t is going to be in seconds because I have taken the lambda value in per second. Is it 5.369? I'll take 5.37 into 10 to the power 9 seconds.
So in the earlier question, what did you mean by the CS particle will recoil?
Sorry?
In the earlier question,
Yeah.
you said the momentum is conserved and the CS particle will recoil. What do you mean by that?
Now, when an explosion happens, let's say there is a particle with a certain mass, let's say 10 kilograms, it is stationary. Let's say it explodes, it breaks into two parts, one of 4 kilograms, the other one is 6 kilograms. So now if this 4 kilogram is, for an example, if it is moving to the right with a momentum of, for an example, let's say 50 Newton seconds, then this 6 kilogram has to rebound with a momentum of 50 Newton seconds for the momentum to be conserved. Am I right? So the original particle that will recoil, the same thing what happens when you fire a bullet from a gun, it recoils because of the momentum is conserved. So the similar way, in the previous questions on barium, but whatever the original one, parent nuclide, when it decay, when it emits a particle, the original one will recoil. So it will also have a kinetic energy. It will also have a momentum. Okay.
Okay, sir.
Right, guys. The next one, 25th one. Hmm? 9.11 into 10 to the power minus 31 mass of an electron. It's an easy one. They are asking you to assume that entire energy is assumed taken by the beta particle. Energy released is 2.6 kilo electron volts. That is 2.6 into 10 to the power 3 to convert kilo electron volts to electron volts into 1. Into 1.6 into 10 to the power minus 90 to convert electron volts to joules equals half into mass of the electron is 9.11 10 to the power minus 31 into V square. So from here you can get the V subjective. Is it 3.02 into 10 to the power 7? Have you got this answer? Start with the next one. 26.
So it's in use, so shouldn't you convert it to kilograms?
Hmm?
Shouldn't you convert it into kilograms?
Yeah. Sorry.
No problem.
Are you getting 7.62 into 10 to the power minus 13 joules? Yes. Are you getting 250,473 years? No? They're asking, determine the time taken in years for 90% of the thorium-230 in a sample to decay to radium-226. So 90% decays means what is remaining is 10%, right? So if I use n equals n naught e to the power minus lambda t, so comparing to the initial number of undecayed nuclei, what is going to remain after the period that they are talking about is 0.1 n naught, 10% of n naught. So I have taken the n to be 0.1 n naught equals n naught into e to the power minus lambda t. Okay, so on either sides, n naughts will cancel off. So 0.1 equals e to the power minus lambda t. Okay, so if I take ln 0.1 equals minus lambda t. Is that clear? Everyone, no? No, you have a problem. Which is the problem? Huh? Okay. So you are not agreeing with the 0.1 n naught, is it? There's a problem there. Okay. You have 1,000 rupees. How much do you have? 1,000 rupees. You spend 90%. You spend? Then how many percent is remaining with you? 10%. 1,000 into 10% is 100 rupees is what remains. Initially, the undecayed number of undecayed nuclei in the sample is n naught. 90% decays. Then what percentage is remaining? 10%. So I'm using the equation n equals n naught e to the power minus lambda t, where n naught is the initial. N naught is the initial number of undecayed nuclei. N is the number of undecayed nuclei in the sample after a time t. So isn't this n supposed to be 10% of n naught? 10% of n naught is 0.1 n naught. So 0.1 n naught equals n naught into e to the power minus lambda t. Then we can cut this n naught and n naught. Then 0.1 equals e to the power minus lambda t. The rest is okay. Is there anyone who don't get this maths part? If 0.1 is e to the
Sir,
power
the
minus,
ln 2 over 75,400. What is that? Sir?
sorry,
So the ln 2 over 75,400. What is that, sir?
wait.
I don't understand that.
Yeah. So ln 0.1 equals minus lambda t. So what is lambda? ln 2 over t half, right? Decay constant. ln 2 over t half. So the t half, the half-life of thorium-230 is given 75,400 years. So I have taken it in years itself because the final answer for t, I need it in years anyway. Okay. So simplify it, you get the answer. We can go for a break. We'll continue after the break. See you in 50 minutes. why can't you? Okay, talk to me after this. Anyway, it will be mailed to you if you want to get it. So it will be mailed to you.
Yeah, then I can go for the next thing was. Sorry. They have some.
There's question 28, page 42. You're right. 28. Cesium-137 is a common product of uranium fission. Very small samples of cesium-137 can be used to calibrate radiation detector equipment. It decays into an isotope of barium by emitting a beta minus particle. Complete the nuclear equation for the decay of cesium-137. So guys, beta minus is -10. So 56 minus 1 is 55 here. And 137 here. Correct. A sample of pure cesium-137 has an activity of 7,400 becquerels. Calculate the mass in kilograms of the sample. The half-life is given. Mass of cesium atom is given. And 1A is in seconds is given. So we can use A equals lambda in. A equals lambda is L into over T half into N. So activity is 7,400 becquerels. L into over T half is half-life is 30.2 years multiplied by 3.15 into 10 to the power 7 to convert it into seconds. Correct? That into N will give you the number of nuclei in the sample. So from here, I can find the N. .0156. into 10 to the power 13 nuclei. But they're asking to calculate the mass in kilograms of the sample. So they have given one atom of cesium-137 is 137 U. So to find the mass, multiply the number of nuclei, 1.0156 into 10 to the power 13. Multiply with the mass of one atom, which is 137 U. So 1 U is 1.66 into 10 to the power minus 27 in kilograms. So we can get the answer in kilograms. .31. Into 10 to the power minus 12 kilograms. Are you getting this answer? Okay. Any questions? People online?
No, sir.
Page 45. Page 45, question 30. Okay. Actinium-225 is a radioactive isotope. It decays to francium by emitting alpha particles. Actinium-225 has a short half-life, which makes it suitable for medical applications. Complete the nuclear equation for this decay. So guys, alpha particle is 2 protons and 4 neutrons. So 225 minus 4 is 221. 89 minus 2 is 87. Have you completed this? You can't find any easy marks than this in the paper. These 2 marks, that's the easiest 2 marks you can get. Okay. Just plus and minus, you get the answer. In a radioactive decay, energy released and the total mass decreases. Show that the energy released if the mass decreases by 1 U is above this much. So E equals mc square. Easy marks again. They're kind like that. But you don't want marks. M is 1 into 1.66 into 10 to the power minus 27 into 3 into 10 to the power 8. That square, that gives you the answer in joules, but we want it in mega electron volts. So divided by 1.6 into 10 to the power minus 19 to get it in electron volts. And again divided by 10 to the power 6 to get it in mega electron volts. It's 933.75 mega electron volts. So they have told about 930. Close enough. Okay. Part C, the francium nucleus and the alpha particle move away from each other after the decay. Now, 2 particles are emitted. I mean, not emitted. The actinium converts to a francium, it decays, and an alpha particle is emitted. So they are saying the francium nucleus and the alpha particle move away from each other after the decay. Explain why the kinetic energy given to the alpha particle is just less than 5.9 mega electron volts. The mass decrease for the decay is given 6.35 into 10 to the power minus 3 U. So guys, 1 U has an energy of 933.75 mega electron volts. 1 U is corresponding to this much of energy. So then if the mass decreases by 6.35 into 10 to the power minus 3 U, then the energy release will be 6.35 into 10 to the power minus 3 U multiplied by 933.75. So the energy released in this decay is 5.9293. 5.929, let's say. Okay. These are energy released in this decay. This is the total energy release. So this total energy release is not only the alpha particles energy. Okay. Like I said earlier, there will be a recoil happening here. So now, when this alpha particle is emitted, let's say to the right, then the francium that will recoil, that will move back in a way that the momentum is conserved. Okay. So if I take the mass of alpha particle to be 4m, the mass of the francium is 221 m. Am I right? Yes or no? So if I consider the momentum to be conserved, if I take the speed of the alpha particle to be V1 and speed of the francium nuclei to be V2 by considering the principle of conservation of linear momentum to the right. Principle of conservation of linear momentum. 4m into V1 minus 221m into V2 is equal to 0, which is the initial momentum, which was 0. Am I right? So simplify this. 4m V1 equals 221m V2. That tells me m and m will cancel off. V1 is 221 over 4 V2. Agree? Okay. Now, I want to find, now I know the speeds. I want to find the kinetic energy of the alpha particle. That's the question, right? Explain why the alpha particle, explain why the kinetic energy given to the alpha particle is just less than 5.9. So I need to find the kinetic energy of the alpha particle and show that it is going to be less than 5.9. Correct? Guys, now, if you see the kinetic energy of the alpha particle, what is the easiest way of doing it? Think about it. Half into 4 into V1 square plus half into. Look at this. I will do it this way. Half into, there will be a little bit of math. Concentrate properly. Half into 4m into V1 square is the kinetic energy of the alpha particle. Agree? Plus half into 221m into V2 square is the kinetic energy of the francium nuclei, which is, the addition is 5.929. Okay. So half into 4m into V1 square is 2m V1 square. Plus half into 221m is 110.5 m. The V2, I will take it from here. V2 is 4V1 over 221. 4V1 over 221. V2. And that needs to be squared. This is 5.929. Okay. Which is 110.5 into 4 square is 60 over 221 square will be 0.036. So this is 2m V1 square plus 0.036 2 m V1 square. This is equal to 5.929. So if I add them together, 2.0362 mv1 square is equal to 5.929. So mv1 square will be 5.929 divided by 2.036, which is 2.912 mega electron volts. Listen, the last bit. Guys, that is the mv1 square. So what is the kinetic energy of the alpha particle? half 4m v1 square, which is 2 mv1 square, which is 2. The mv1 square is what I found, 2.912. So that is 5.82 mega electron volts. So the kinetic energy of the alpha particle is 5.82, little less than 5.9. Someone asked me why you got easy marks in the first part, 6 marks. That's because of this. For the next 4 marks, they will make you work. Fair enough.
So can you go to next page, please?
Those who deserve it will get it.
Excuse me, sir.
Yes.
Sir, to convert joules into electron volts, you multiply or divide? To convert joules into electron volts, do you multiply or divide?
You need to convert joules to electron volts. You need to divide by 1.6 into 10 to the minus 90.
But if you convert electron volts to joules, you have to multiply, right?
Correct.
Okay.
But here I haven't made any joules involved. We have
Yeah.
completed dealt with mega electron volts. Okay.
Yes.
Okay. So that's mv1 square. Then the kinetic energy of the alpha particle is half into 4m into v1 square, which is 2m v1 square. That will be 2 into 2.912, which is 5.82. Little less than 5.9. Okay. Right, guys. Mark a few more for homework 32. 33. $35. Only the part A. 37. 39. 40. Yeah, that's it. So we'll discuss these on the next day, and next class we will, if the time permits, we will start with the next topic, which is either oscillations or astrophysics, one of those two. Those are the only two topics remaining for us to complete the syllabus. So anyway, tomorrow we are having a unit 4 test, okay, at 9 in the morning. Be here by 8:50. Bye people, see you, take care.
Thank you, sir.
Thank you, sir. Bye.